The ground beneath you is moving at this very moment. We will uncover 25 geological clues that predict the next great continental collision, giving you the power to see the future shape of our planet. Together, we will learn to read the hidden language of shifting continents and rising mountains. What ancient signals are buried deep within the rock? And how can a tremor today foretell a mountain range 10 million years from now? What does it feel like to stand on a landscape that is secretly in motion? This grand rhythm of our planet operates on a timescale almost impossible to grasp. Think of it as Earth's slow, steady heartbeat, a pulse that lasts not for seconds but for hundreds of millions of years. The crust we build our lives upon is merely the surface of a far more active world. It is a collection of colossal rafts, some bearing entire continents, endlessly adrift on a sea of slowly churning rock. These tectonic plates are in perpetual motion, driven by the immense heat simmering deep within the planet's core. Their movement is the engine of this epic cycle. For a time, they drift apart, creating vast new ocean basins between them, but the journey does not end there. Eventually, the direction of their slow march reverses, and these continental fragments are drawn back together by the very forces that pushed them apart. They converge in a slow-motion collision of unimaginable power, welding themselves into a single, monumental landmass. This is the supercontinent, a temporary monument in geological time. The last one, Pangaea, assembled over 300 million years ago, uniting almost all of Earth's land into one sprawling supercontinent before it, too, began to fracture. This is not a one-time event but a recurring loop, the Supercontinent Cycle. Grasping this immense, rhythmic dance is the first and most vital step. It transforms our search for clues from a random scavenger hunt into a deliberate investigation. We are not just looking for odd rocks or strange tremors. We are learning to read the current chapter in this billion-year-old story, to understand where we are in the cycle right now, and to predict what breathtaking geographical change the next chapter will bring. That geological sprint is precisely what our satellites are now detecting. We can watch the continents creep across the globe in real time, their movements tracked down to the millimeter by a network of orbiting eyes and ground-based lasers. This is not a vague estimation. It is a direct, precise measurement of our planet's restlessness. Normally, a tectonic plate moves at about the same speed your fingernails grow, perhaps 2 or 3 centimeters each year. But when a plate suddenly accelerates, doubling or even tripling its pace, it sends a clear signal through the entire geological community. This is one of the most straightforward clues we have. A continent is not just drifting, it is being pulled with purpose, drawn toward a fateful meeting. The most famous historical example of this was the Indian subcontinent, which raced northward at an incredible pace, perhaps as fast as 15 centimeters per year, before it slammed into the underbelly of Asia. That impact is not a closed chapter in a history book. It is an ongoing event, a relentless push that forces the Himalayas a little higher with every passing year. So when our instruments detect a similar surge in velocity today, it begs a compelling question. Which continent is now entering its own sprint, and what new mountain range might that velocity one day build? This rumbling is the planet's own early warning system. While satellites track the surface movement, a different kind of signal comes from deep below, a constant low-frequency hum of strain and release. The second major clue in our investigation is a clear pattern of intensified seismic activity along the margins of converging plates. These are not the random, isolated tremors that occasionally shake a region. This is something far more organized and telling, Imagine the sound of a great wooden ship under immense stress, its timbers groaning and cracking as it is pressed from all sides. That is what we are listening for in the Earth's crust. As two continental plates move toward each other, the oceanic crust between them often has no place to go but down, sliding beneath the overriding plate in a process called subduction. This is not a smooth, silent descent. It is a violent, grinding struggle, and the friction generates earthquakes. The deeper these quakes occur, the further the subducting slab has plunged into the mantle, outlining its ghostly shape on our seismographs. By carefully mapping the clusters of these deep focus quakes, scientists can literally trace the outline of the descending plate. They can see the angle of its dive and the tremendous pressure building along this underground battlefront. This seismic map does more than just show us where the Earth is cracking today. It reveals the exact location where the continents, carried on these colossal plates, are destined to finally meet and lock together, beginning the slow, monumental process of building a new mountain range for a future world. This subtle buckling of the land is our third major clue, a slow-motion preview of the drama to come. Even before two continents meet in their final, monumental crash, the ground between them begins to groan and rise. The immense forces of convergence act like a colossal vise, slowly squeezing the crust. The result is not a sudden, jagged mountain range, but something far broader and more subtle. Vast regions of land begin to uplift, creating what geologists call pre-collision orogenic belts. These are the earliest wrinkles on the planet's skin, a gentle folding and swelling that signals the tectonic pressure is already building. Imagine pressing on the edge of a thick rug. Long before it crumples into a sharp peak, the entire section ahead of your hand will begin to arch and rise. That is precisely what happens to the Earth's crust. This gradual uplift can be measured from space with incredible precision using satellite altimetry, which maps the changing elevation of the landscape down to the millimeter. On the ground, field geologists study these warped rock layers, reading the story of immense pressure written in stone. These broad, elevated highlands are a clear warning. They tell us that the slow-motion collision has already begun its opening act, and that the main event, the birth of a new mountain range for a future world, is still millions of years in the making. Deep within the foundation of every continent, a silent compass is always pointing the way. Ancient volcanic rocks, as they cool from liquid fire into solid stone, lock in a tiny but permanent record of the Earth's magnetic field at that exact moment. They become geological time capsules, preserving the direction to the magnetic North Pole from millions of years ago. This frozen record is our fourth clue, the science of paleomagnetism. When a continent is drifting serenely on its own, the magnetic signatures in its rocks tell a relatively simple story, a steady path of movement. But as it nears another massive landmass, something changes. The continent is no longer just moving forward, it is being pushed, pulled, and twisted by the colossal forces of convergence. Scientists can detect this by studying long sequences of rock along a continental margin. They often find a dramatic kink or a sharp curve in what should be a smooth path, an abrupt shift in the apparent wander of the ancient pole. This magnetic fingerprint is irrefutable evidence. It tells us the entire continent is undergoing a profound change in its trajectory, like a great ship suddenly altering its course. It is rotating or shifting its latitude with new purpose, pulled by the immense gravitational tug of its impending rendezvous. This is not a subtle hint. It is a clear signal written in stone, a declaration that the slow dance of the continents has entered a new and more decisive phase. Even the planet's own pull of gravity holds a secret message. The force that keeps our feet on the ground is not the same everywhere on Earth, and these subtle variations form our fifth major clue. Sophisticated satellites can measure these minute differences, mapping a hidden landscape of gravitational highs and lows. Where a dense, heavy oceanic plate is forced to dive beneath a lighter continental plate, it creates a distinct negative gravity anomaly. In this zone, the gravitational pull is slightly weaker, a subtle dip that our instruments can detect from space. This is the ghostly signature of the descending slab, a mass of cold, dense rock sinking into the warm mantle. At the same time, the overriding continental plate often shows the opposite effect, a slight positive gravity anomaly caused by the immense pressure that is already beginning to thicken and crumple its crust. Together, these gravitational fingerprints chart the unseen architecture of the collision zone. They allow us to map the deep structure of the converging plates, revealing the subterranean battle lines long before the main conflict breaks the surface. It is an incredible thought that we can essentially feel the immense weight of future mountains, sensing their buried foundations pressing down from below, long before their peaks ever pierce the sky. The very rocks themselves change their character under the immense strain. Deep below the surface, in the crushing darkness where continents converge, ordinary stone is reborn. This transformation gives us our sixth clue, the silent testimony of metamorphic rock belts. When the Earth's crust is caught in a tectonic vise, the minerals within it can no longer remain the same. They are subjected to such fantastic pressures and temperatures that they are forced to rearrange their very atomic structure, becoming entirely new kinds of rock. It is a process of profound geological alchemy, and the specific minerals that form are like a fingerprint, revealing the exact conditions of their creation. In the specific environment of a subduction zone, where a cold, dense oceanic plate is forced to dive into the mantle, a unique set of minerals can crystallize. These are high-pressure, low-temperature rocks, most famously the beautiful and rare blue schists. Their distinctive blue hue comes from minerals like glaucophane, which can only form in that narrow window of incredible pressure without the accompanying high heat. Finding these rocks at the surface is like finding a message in a bottle from a journey to the underworld. They tell a story of being dragged deep down, perhaps tens of kilometers into the earth, and then, miraculously, being pushed back up to the light. This cycle of deep burial and subsequent exhumation is a hallmark of an active subduction zone. These exotic rock belts are the physical evidence that the great tectonic engine is not just idling, it is actively running, preparing the raw materials and the compressed foundation for the continental main event still to come. A chain of volcanoes can begin to walk across the landscape. This strange migration is our seventh clue, a fiery signal of the shifting forces deep below. Volcanoes are not random features, they form in precise lines called arcs, tracing the surface expression of a deeply subducting plate. As the oceanic plate dives into the mantle, it releases water that lowers the melting point of the overlying rock, generating the magma that feeds these volcanoes. But this entire system is dynamic. When a continent approaches this subduction zone, its buoyant, unyielding crust acts like a log about to be fed into a wood chipper. It resists being pulled down. This resistance can change the angle of the descending slab, or even slow its entire descent. As that geometry shifts, so too does the location where the magma is generated. The result is that the entire volcanic arc, the line of fire itself, can begin to migrate, slowly marching across the continent. Geologists can read this history in the rocks, dating extinct volcanoes that were once active and mapping their positions relative to the modern arc. A migrating arc is a clear warning. It means the subduction zone is being stressed, its parameters changing under the new tectonic regime. In some cases, the approach of the continent can choke the system entirely, causing the volcanoes to fall silent and go extinct. That silence is itself a deafening announcement. It signals that the oceanic plate is no longer able to descend freely, that the continent has arrived at the trench, and that the stage is now set for the main event, a direct continental collision that will reshape the world. The story of a coming collision is written in mud and stone. Long before mountains rise, the very ground begins to whisper its secrets, and we find these whispers preserved in the vast, layered archives of sedimentary basins. These are the eighth clue in our investigation, a geological diary that records every subtle shift in the landscape. When a continental margin is passive and stable, far from any tectonic drama, the sediment that accumulates is fine and quiet. It settles in deep, calm waters, building layers of mud and silt that speak of a long, peaceful era. But that peace is shattered when compression begins. The sediment record tells this story with stunning clarity. Suddenly, the fine muds are replaced by coarse, jagged conglomerates and thick sandstones. These are not the sediments of a quiet sea. They are the rubble of a landscape being violently torn apart, the debris of newly rising highlands carried by powerful rivers to the basin's edge. It is as if the geology itself has switched from a gentle whisper to a roaring shout. The shape of the basin itself transforms under the growing pressure. Instead of a symmetrical bowl, it becomes a deep, asymmetrical trough, its layers thickening dramatically toward the future mountain belt. This is the crust warping downward, creating a massive depression that eagerly captures every piece of rock eroded from the rising land. By drilling cores deep into these basins, scientists can read this history like the pages of a book. They can pinpoint the exact layer where the sediment changed, the very chapter in Earth's history when the landscape first began to transform in anticipation of a colossal impact still millions of years away. These sedimentary archives do not just record the past, they foretell the future, revealing the slow, deliberate preparations for a new world in the making. Scattered along the spine of a mountain range, you might find a puzzle made of dark, dense rock that seems utterly out of place. These are Ophiolites, the ninth and perhaps most dramatic clue in our search. They are nothing less than fragments of an ancient ocean floor, great slices of the Earth's deep crust and upper mantle that have been ripped from their home and thrust up onto the continents. To hold a piece of an Ophiolite is to hold a relic of a lost world, a sea that vanished millions of years ago. Their preservation is a rare and precious event, a geological miracle that only occurs during the most violent tectonic finales. When two continents finally collide, the ocean basin between them is destroyed, but its story is not entirely erased. In the ultimate closing act, slivers of that oceanic lithosphere are scraped off and pushed upward, often emplaced directly onto the continental margin like a trophy of the tectonic war. These Ophiolite suites become the definitive marker of the suture zone, the scar in the Earth's crust where two landmasses have permanently welded themselves together. By mapping these sequences, geologists can trace the ghostly outlines of long-dead oceans and identify the precise line of impact from collisions that shaped our world in the deep past. But this knowledge does more than illuminate history. It gives us a template for the future. When we recognize the specific geological environments and rock associations that create Ophiolites, we can look at active subduction zones today and identify the places most likely to produce a new suture zone millions of years from now. The presence of these oceanic relics is a powerful declaration, signaling the death of one great seaway and the imminent birth of the next great mountain chain. A network of silent sentinels is now measuring the very breadth of the planet. Our 10th clue comes from a global web of ultra-precise GPS stations. a technology known as Geodesy that tracks the infinitesimal bending and stretching of the Earth's crust. In the calm before the tectonic storm, these instruments reveal something startling. The ground is not gliding smoothly toward its destiny. It is stuck, locked in place by immense friction, while the deeper forces below continue to push. This creates a slow, relentless compression, a storing of elastic energy in the crust itself. Picture a giant spring being coiled tighter and tighter, millimeter by millimeter, year after year. That is precisely what is happening along the margins of converging continents. Geodesy allows us to measure this crustal shortening and shear strain with astonishing accuracy, giving us a real-time gauge of the tectonic forces gathering deep underground. We can actually quantify the amount of energy being stockpiled, energy that must one day be released. This is not a vague prediction. It is a direct measurement of the future, a calculation of the violent earthquakes and the dramatic uplift that will eventually reshape the landscape. These silent, accumulating numbers paint the most vivid picture possible of a continent under immense and growing stress, holding its breath before the great collision begins. These subterranean scans reveal a planet in constant, churning motion. Our 11th clue comes from a revolutionary technology that peers deep into the Earth's interior, a technique known as seismic tomography. Just as a medical CT scan constructs a three-dimensional image of the human body using X-rays, seismic tomography builds a picture of the mantle by tracking the speed and paths of thousands of earthquake waves as they journey through the planet. These waves travel faster through cold, dense material and slower through hot, buoyant rock, allowing scientists to map vast structures hidden from view. The resulting images are nothing short of breathtaking. They show colossal, slumbering slabs of ancient ocean floor, now cold and heavy, sinking like great stone anchors through the warm plastic mantle. These are the ghosts of vanished oceans, their lithosphere subducted millions of years ago, yet still plunging toward the planet's core. The specific geometry of these descending slabs is a direct window into the tectonic engine. When we see a long, continuous slab diving at a steep, clean angle directly beneath the edge of a continent, it tells a very specific story. This is the signature of a mature, well-established subduction zone, an efficient conveyor belt that has been consuming oceanic crust for eons. It is this relentless downward pull that is the primary force drawing continents together. A steeply plunging slab acts like a powerful gravitational anchor, creating a suction in its wake that pulls the entire tectonic plate behind it, setting the stage for the final continental approach. By analyzing these deep Earth portraits, we gain an unobstructed view of the converging forces that are, at this very moment, sculpting the next chapter of our world's geography. The very distribution of life itself holds a geological secret. Our 12th clue comes not from the rocks alone, but from the ancient plants and animals whose fossilized remains are entombed within them. This is the principle of biogeographic provincialism, a biological map of a world in motion. When continents are isolated by vast, impassable oceans, evolution takes its own unique course on each landmass, creating distinct provinces of life. Imagine a world where Australia's unique marsupials evolved in complete separation from the placental mammals of Asia for tens of millions of years. That isolation is a direct result of continental geography. But as continents converge, this biological map is violently redrawn. The ocean basin that once served as an impenetrable barrier begins to narrow, allowing the first tentative land bridges to emerge. The fossil record captures this moment with stunning clarity. We see the sudden appearance of new species in regions where they never existed before, a clear sign of migration across a newly formed corridor. Conversely, we find evidence of a single, widespread species being split into two isolated populations as a new seaway opens, forcing them to evolve along separate paths. This great shuffling of life forms preserved in stone provides independent biological corroboration of the physical closing of an ocean basin. The story of life becomes inseparably intertwined with the story of the land, revealing not just the fact of a continental rendezvous, but its precise timing and growing proximity. The migrations of long-vanished creatures now serve as a living clock, ticking down the millions of years until the next great collision. A shift from tropical cold to desert salt reveals a continent on the move. Our 13th clue is written not in the violent tremors of the Earth, but in the quiet, accumulated memory of its ancient climates, a field known as paleoclimatology. The rocks beneath our feet hold a detailed diary of the weather that shaped them millions of years ago. Thick layers of evaporites, the crystalline remains of vanished salt lakes and seas, tell a story of relentless sun and arid deserts. Lush coal seams compressed from ancient swamp forests speak of a humid, tropical world drenched in rain, and the scattered, scratched boulders of glacial till are the unmistakable calling card of an icy wasteland. Each of these deposits is a fossilized weather report, a permanent record of the climate at a specific point in deep time. As a continent drifts across the globe, its latitude changes, and it inevitably journeys through these different climate zones. By carefully reading the vertical sequence of these climate-sensitive rocks along a continental margin, scientists can reconstruct an entire voyage. They can trace a continent's path from the steamy equator to the temperate mid-latitudes, or even all the way to the frozen poles. A dramatic and rapid shift in this climatic succession is a powerful signal. It means the continent is not just drifting aimlessly, it is being pulled with purpose into a new latitudinal belt, often because it has entered the gravitational influence of a converging plate. This changing climate, locked in stone, becomes one of the most elegant and compelling pieces of evidence, proving that the land is on a direct and determined course for a future impact that will redefine its shores. A single grain of sand can hold the memory of a lost continent. Among the countless minerals eroded from mountains and carried to the sea, one stands out for its incredible durability and its precise internal clock. This is zircon, a tiny crystal that forms in cooling magma and becomes a nearly indestructible time capsule. Zircons are so tough they can survive multiple cycles of mountain building, erosion, and sedimentation, carrying their original age through hundreds of millions of years. Our 14th clue is the science of Zircon Geochronology and provenance, a way of reading the deep history written in these microscopic grains. When geologists study a sedimentary basin, they do not just look at the rock as a whole. They carefully separate these individual zircon crystals and measure their precise ages. The result is a population age spectrum, a kind of demographic profile of the ancient landscape that supplied the sediment. For millions of years, a continental margin might show a consistent, familiar age pattern, reflecting the local, ancient mountains that have always been its source. But then, something remarkable happens in the geological record. A new population of zircons suddenly appears, their ages completely foreign to the local geology. These crystals tell a different story, one that originated in a distant, alien terrain. This sudden appearance is a profound revelation. It means that a new landmass, a continent that was once an entire ocean away, has now moved close enough that its rivers are beginning to pour sediment into the same basin. The ancient barrier of the sea has been breached. This change in sediment provenance is an exquisitely sensitive detector, pinpointing the exact moment in deep time when a new and formidable player first entered the geological scene, signaling that the Great Collision is no longer a distant possibility, but an approaching certainty. The very engine that builds the ocean floor can also fall silent. Deep beneath the waves, a system of underwater mountain ranges known as mid-ocean ridges acts as the planet's primary crust factory. Here, magma from the mantle wells up, cools, and solidifies into new oceanic crust, which is then steadily pushed away from the ridge like a colossal conveyor belt. This constant creation is the fundamental force that drives plates apart. But this system is not always in perfect balance. Our 15th clue is a profound shift in this rhythm, a significant slowdown or even a complete cessation of spreading at a ridge adjacent to a closing ocean basin. When this happens, it signals a critical turning point in the tectonic story. The subduction zone on the other side of the ocean is consuming the old sea floor so voraciously that it is pulling the plates apart faster than the ridge can create new material. It is a race the ridge cannot win. The conveyor belt is being pulled from its far end, and the factory at its source begins to stall. This imbalance is the clearest possible sign that the ocean basin is in its death throes. The room between the approaching continents is vanishing, consumed by the insatiable subduction zone. With no new crust being added to widen the gap, the two landmasses are drawn inexorably closer, their final meeting now a matter of geological certainty. The silence of a dying ridge is a quiet but definitive announcement that the stage is set for a collision that will close an entire ocean. A continent can bend like a plank of wood suspended over an abyss. This astonishing flexibility is our 16th clue, a phenomenon known as Lithospheric Flexure. We often think of continental crust as a solid, unyielding block, but on a planetary scale, it behaves more like a rigid yet flexible plate. When a dense, heavy oceanic plate dives into the mantle, it does not simply vanish. It pulls down on the edge of the overriding continent with immense gravitational force, causing that entire margin to warp downward. The result is a deep, trough-like depression called a foredeep basin, a moat that forms directly adjacent to the rising volcanic arc. We can measure this bending with incredible precision through seismic reflection studies, which act like a sonogram for the Earth, revealing the geometry of the warped rock layers deep below. The very shape of this flexure tells a vivid story. The wavelength, the broad distance over which the bending occurs, and its amplitude, the depth of the downward curve, are not random. They are a direct readout of the forces at work. A deeper, broader flexure indicates a stronger pull from a heavier subducting slab and a more rigid continental plate resisting the bend. This makes the lithosphere itself a colossal strain gauge, visibly deforming under the load of the converging tectonic system. Observing this slow, monumental sag in the continental crust is like watching the bow of a great ship dip as it begins to take on a colossal, unseen weight, a clear sign that the forces of collision are already taking their toll. Planet's own internal warmth tells a story of what lies beneath. The flow of heat from the Earth's interior is not uniform, and these subtle thermal whispers form our 17th clue. Deep within an active subduction zone, a fascinating thermal paradox unfolds. The cold, dense slab of the oceanic plate, as it plunges into the mantle, acts like a giant heat sink. It chills the overlying continental plate, creating a distinct and measurable zone of low heat flow at the surface. This cold shadow is a clear thermal signature of a system in motion. But as the continental collision draws near, this pattern begins to shift. The subduction process starts to slow, choked by the arrival of the buoyant, unyielding continent. With a great refrigerating slab no longer descending efficiently, its cooling effect diminishes. At the same time, the crust itself is being squeezed and thickened by the relentless convergence. This thickened crust acts like a warm blanket, trapping the heat generated by the natural radioactive decay of elements within the rocks. The result is a gradual but significant warming of the entire continental margin. Scientists can map these heat flow anomalies with sensitive instruments, creating a thermal portrait of the lithosphere. A previously cold region that begins to warm is sending a powerful signal. It suggests the tectonic gears are shifting, that the subduction engine is stalling, and that the continental crust is preparing for the main event. This change in the Earth's thermal pulse is a profound indicator, revealing that the slow-motion collision is not just a physical process, but a thermal one as well, fundamentally altering the very energy of the landscape. The very chemistry of fire and stone can reveal a continent's fate. Magma is not a single, uniform substance. Its character is shaped by the deep sources from which it is born. When a tectonic plate descends into the mantle, it typically generates magma by melting the overlying rocks of the Earth's interior, creating a specific family of volcanic rocks with a predictable chemical identity. But this system is transformed when a continent arrives at the subduction zone. The continent's crust is far thicker, older, and richer in silica and other light elements than the oceanic crust or the mantle. As the colossal forces of convergence squeeze this continental margin, its deepest roots can themselves begin to melt. This creates a new hybrid magma, a blend of material from the Earth's deep interior and its ancient, buoyant crust. This mixing leaves an unmistakable calling card, a distinct geochemical fingerprint locked within the resulting igneous rocks. Scientists can read this fingerprint by analyzing specific ratios of isotopes, such as strontium-87 to strontium-86, or neodymium-143 to neodymium-144. These ratios act like a geological DNA test, revealing the precise ancestry of the magma. The sudden appearance of these unique signatures in volcanic lavas or the vast, cooled chambers of granite plutons is a profound development. It signals that the continent is no longer just a passive observer on the edge of the subduction zone. It has now become an active, melting participant in the system. This chemical shift marks a critical turning point, the moment when the continent is no longer approaching the collision, but is actively being consumed by its preparatory fires, a clear herald that the final continent-to-continent impact is imminent. The rocks themselves begin to fold and break under the immense, invisible pressure. Our 19th clue is written in the very architecture of the crust, in the massive fractures and colossal overlaps known as thrust fault systems. These are not simple cracks in the ground. A thrust fault is a gargantuan rupture where one entire block of the Earth's crust is forced up and over another, like a giant sliding a great rug over a wooden floor. The development of these large-scale faults is the definitive structural signature of a continent in compression. Geologists become detectives of this deep time stress, meticulously mapping the orientation, sequence, and shear displacement of these faults. Each one is an arrow pointing toward the source of the pressure. When a series of these thrust faults begins to form, not just at the coastline, but progressively farther inland, it sends an unmistakable message. The deformation is propagating, marching steadily into the heart of the continent. This is the crust actively preparing for the main event, thickening itself by stacking great slices of rock one on top of the other. The sequence of these faults tells a story of escalating force. Older, deeper faults are often reactivated, while new ones break through previously stable ground. By reading this structural diary, scientists can reconstruct the direction and magnitude of the tectonic vise, quantifying the awesome power that is slowly, methodically, building the foundation for a future mountain range. This propagating wave of fractures is the continent's own skeletal framework being reshaped in real time, a clear signal that the Great Collision is no longer a distant forecast, but a geological reality already transforming the land. Even the global ocean feels the pull of colliding continents. Our 20th clue reveals a planetary scale consequence, a shift in the very level of the sea itself. This phenomenon, known as eustatic sea level change, connects the slow dance of the continents to the shorelines of the entire world. The process begins with the creation of a new supercontinent and its accompanying mountain ranges. These colossal features are unimaginably heavy, and their immense weight literally pushes the continental crust down into the underlying mantle, much like a heavy ship sits lower in the water. This regional depression, however, is only part of the story. The ultimate collision that builds the mountains also destroys the vast ocean basin that once separated the landmasses. Think of the ocean as a fixed amount of water in a bathtub. If you push a large, heavy object into the tub, the water level rises. But if you also remove a section of the tub itself, making the container smaller, the water has less space to fill and its level falls. This is precisely what happens during a supercontinent assembly. The closing of an entire ocean basin reduces the total volume available for seawater, causing the oceans to retreat from coastlines across the globe. In the geological record, we find evidence of these great marine regressions, periods when shallow seas drained from the interiors of continents, leaving behind vast plains of sedimentary rock that were once the seafloor. Identifying a major regression that coincides with all the other evidence for a collision provides the final, global context. It demonstrates that the event was not a local geological drama, but a planetary transformation, an upheaval that literally reshaped the face of the entire Earth, altering the map for every living thing on the planet. The ocean floor holds a secret tape recorder, one that has been running for hundreds of millions of years. Our 21st clue lies in the remnant magnetism locked within the dark, volcanic rock of the oceanic crust. As this new crust forms at the fiery mid-ocean ridges, iron-rich minerals within the lava align themselves with the Earth's magnetic field, freezing that exact orientation in time as the rock solidifies. Since our planet's magnetic field reverses its polarity at irregular intervals, the result is a stunning geological artifact. The ocean floor becomes a colossal tape recording, a symmetrical barcode of magnetic stripes, with each stripe representing a chapter in Earth's magnetic history. Vessels towing sensitive magnetometers behind them, like underwater metal detectors, can map these invisible stripes across entire ocean basins. This magnetic survey reveals a profound and beautiful pattern. On either side of a mid-ocean ridge, the stripes are mirror images, with the oldest crust farthest from the ridge and the youngest right at the volcanic center. But when an ocean is destined to close, this perfect symmetry tells a different story. The entire pattern of magnetic anomalies will appear progressively younger as you approach one specific continental margin. This is the telltale sign that the ocean floor is being consumed, conveyor belt style, into a subduction zone, the point where the very youngest magnetic stripe vanishes beneath the continent is the precise leading edge of the collision. It is the finish line for the ocean and the starting line for the birth of a new mountain range. By reading this magnetic barcode, scientists can perform a simple calculation. They can measure the distance from that subduction point back to the opposite continent and divide it by the current rate of plate motion. The answer is a countdown clock, giving us the number of millions of years remaining before these two great landmasses finally meet. A river's journey carries more than just water. It transports the ground-up history of entire mountain ranges. Our 22nd clue lies in the smallest fragments of that history, the diagnostic detrital minerals found within ordinary sand and mud. When a continent is stable and quiet, the sediment washing into its coastal basins is equally unremarkable. composed of common minerals like quartz and feldspar that tell a simple story of gentle erosion. But the approach of a colossal collision changes everything. Suddenly, within the layers of a sedimentary basin, geologists can find something astonishing: tiny grains of high-pressure metamorphic minerals like coesite or even microscopic diamonds. These are not ordinary components of sand. They are the survivors of an incredible journey. Minerals like coesite can only form at depths of nearly 100 kilometers, under pressures so immense they rearrange the very atomic structure of common rock. For such a grain to end up in a riverbed, it had to be part of a rock that was dragged to these staggering depths within a collision zone, and then, through the immense forces of uplift, pushed all the way back to the surface where erosion could finally set it free. Finding these minerals in a sedimentary layer is like finding a splinter of a cathedral window in a pile of common gravel. It is a direct, tangible message that a major mountain-building event is not just a future possibility, but a present reality. It tells us that a fully formed orogenic belt, the product of a continental collision, is already standing tall somewhere upstream, actively being weathered away and spreading its unique, deep earth signature across the surrounding landscape. This sudden appearance of exotic minerals in the sediment record is one of the most spectacular and definitive clues, providing undeniable proof that the tectonic battle has already been fought and won, and that the new mountains have begun to tell their own story. From high above, a new kind of eye is watching the continents breathe. Our 23rd clue is a technology that transforms the entire planet into a living, moving canvas. Interferometric synthetic aperture radar, or INSAR, uses a series of satellite passes to measure the distance to the ground with an accuracy down to the millimeter. By comparing these radar images over time, it creates stunning maps of deformation, painting the landscape in swirling, rainbow-colored fringes. Each hue shift represents a subtle sinking or rising of the Earth's skin. In regions destined for collision, these maps reveal a breathtaking spectacle. They show vast, broad areas of the crust actively arching upward, while adjacent zones may be slowly sagging downward, all in response to the immense tectonic vise slowly tightening deep below. This is not a single snapshot. It is a live-action movie of continental stress, frame by frame, year by year. We can actually watch the strain accumulate silently across hundreds of kilometers, visualizing the elastic energy loading into the crust like a spring being coiled. These intricate interference patterns make the invisible, relentless process of convergence starkly visible. They provide a direct, real-time view of the planet's crust buckling and bending in preparation for the main event, giving us an unprecedented window into the forces that are, at this very moment, sculpting the mountains of a future world. A forest can hold the memory of a lost world in the imprint of a single leaf. Our 24th clue takes us from the grinding of rock to the quiet world of ancient plants to the field of paleobotany. The fossilized remains of ancient flora are far more than just pretty shapes in stone. They are exquisitely sensitive environmental barometers, each species adapted to a specific range of temperature, rainfall, and seasonal change. When we find the very same fossilized trees, ferns, and flowering plants preserved in rocks on continents now separated by thousands of kilometers of open ocean, the conclusion is inescapable. These now distant lands were once neighbors, sharing a unified climate and a continuous ecosystem. It is as if you found two pages from the same book, one in North America and one in Europe, and realized they were once part of a single, unbroken volume. The Glossopteris flora is a classic example, with its distinctive tongue-shaped leaves found scattered across South America, Africa, Antarctica, and India. This widespread distribution was one of the earliest and most compelling pieces of evidence Alfred Wegener, used to support his theory of continental drift. But this evidence goes beyond just proving ancient connections. It provides a sensitive biological clock for the collision process itself. As continents draw near, their previously isolated floras begin to mingle. In the fossil record, we can trace this migration. We see the sudden arrival of new plant species, invaders from the approaching continent, appearing in the sediment layers. By carefully dating these layers, scientists can pinpoint the exact moment the land bridge formed, the precise geological instant when the sea barrier was finally breached and the two worlds of life became one. The silent, patient journey of spores and seeds thus writes a detailed timeline of convergence, marking the final steps before two continents become locked in an embrace that will last for eons. We can now build the future in miniature, using the very laws of physics to peer millions of years ahead. This final, 25th clue is where all the threads of our investigation converge in the realm of numerical and analog modeling. Geologists construct these intricate simulations both as complex computer code and as scaled-down physical experiments in laboratories. They are not mere guesses, they are rigorous tests. Every piece of data we have gathered, from the precise velocity of the plates measured by satellites to the deep strength of the rocks revealed by seismic waves, is fed into these digital crucibles. The models then calculate the immense forces at play, simulating the slow, grinding dance of continents across countless virtual millennia. The true power of this method is revealed when a simulation's final state perfectly mirrors the geological reality we observe today, from the placement of a mountain range to the angle of a fault line. A model that can accurately recreate the past has earned the right to predict the future. By running these verified simulations forward, scientists can generate a spectrum of plausible scenarios for the next great continental collision. They can watch as Africa slowly closes the Mediterranean, or as Australia merges with Southeast Asia, visualizing the birth of new mountain chains and the closing of ancient seas. This is the ultimate synthesis, a forecast built not on a single clue, but on the integrated story of all 24. It transforms our detective work into a tangible vision, allowing us to witness the next great act in our planet's endless geological drama before the first rock has even begun to rise. So we arrive at the final synthesis, weaving 25 distinct threads into a single, breathtaking tapestry of the future. The clues are no longer scattered pieces of a puzzle. They are a chorus of data, all singing the same epic song of convergence. From the millimeter-by-millimeter creep of GPS stations to the deep Earth portraits painted by seismic tomography, from the exotic minerals in river sands to the migrating fossils in ancient rock, every signal points toward the same impending geological destiny. The most powerful forecast to emerge from this symphony of evidence is the slow, relentless collision between the African and Eurasian plates. This is not a sudden event, but a continuous process that has been unfolding for millions of years and will continue for millions more. The Mediterranean Sea, a beautiful remnant of the ancient Tethys Ocean, is living on borrowed time. Our integrated clues tell us it is destined to close forever, squeezed out of existence by the unyielding march of the continents. In its place, a new mountain range will be forged, a chain so vast it has been given a prophetic name, the Mediterranean Mountains. This future range will not rise from a single, clean impact. It will be a complex mosaic, built from the gradual incorporation of smaller landmasses and island fragments, like Italy and Greece, being pressed and sutured onto the mainland. This grand synthesis demonstrates that the future of our planet is not a mystery. It is a story already being written in the language of strain, stone, and deep time, a narrative we have now learned to read. From the subtle flexing of the lithosphere to the dramatic upheaval of mountain belts, These 25 geological clues provide a powerful toolkit for peering into Earth's future. They reveal a planet in constant dynamic motion, where the slow but irresistible forces of plate tectonics continue to reshape our world. The next great continental collision is not a matter of if, but when and where. By learning to read these signs, we gain not only a deeper appreciation for our planet's history, but also a profound understanding of the forces that will define its future landscapes. The Earth story is still being written, and now you know how to read the next chapter.